SysML v2 Lesson 7 Composition and Specialization. Welcome back. In this lesson, we'll look at two fundamental concepts in SysML v2. How to define that one element structurally owns another, which is composition, and how elements inherit and restrict features from more general elements, which is specialization. Together, these concepts form the parts tree, a logical hierarchy where specific parts establish an owning membership within a broader system definition, and variant elements are defined as specialized versions of others. To be precise, SysML v2 uses specialization as an umbrella term, but strictly distinguishes between two specific applications. One is subclassification, when a definition inherits from a more general definition, and subsetting, when a usage inherits and restricts a more general usage. SysML v2 introduces a major shift in how we interact with these hierarchies, a standardized textual notation. Let's look at how this provides a powerful alternative to traditional diagramming. In SysML v1, ownership was primarily expressed diagrammatically using a composite association, a line with a solid black diamond on the parent side. So, to show that a vehicle owns an engine on a diagram, you draw this. In SysML v2, the graphical notation is preserved. You can still draw blocks and solid black diamonds to show composition. However, SysML v2 introduces a perfectly equivalent textual notation where ownership is established by nesting elements inside curly braces. Here's what that exact same composition looks like in code. The semantic rule is simple. When an element is declared within the body, or the curly brackets, of a namespace like a definition, it establishes an owning membership relationship, making it an owned feature of that parent definition. The textual structure directly mirrors the containment tree. You no longer have to rely exclusively on tracing lines across complex graphical diagrams to understand system composition. You can simply read the textual nesting. This results in an alternative modeling experience where the hierarchy is always visible, local, and mathematically unambiguous. Now let's look at how this plays out in an example. Here, we're going to model a vehicle hierarchy, a generic base definition, and a specific variant called sports car, demonstrating both subclassification and subsetting in action. Engine, V8 engine as a subclassification of engine, which is a definition specializing a definition, and wheel. Then we define the abstract base, which is the vehicle, with two abstract part usages, engines and wheels. These are architectural placeholders that declare any vehicle must have at least one engine and at least two wheels, leaving the specific configurations to the variant. Then we define sports car, which subclassifies vehicle. Because sports car inherits the features of vehicle, it implicitly inherits the abstract usages. Here is where subsetting does its work to refine those usages. The part usage car wheels is declared as 4 wheels and explicitly subsets the inherited wheels usage. This restricts the parent's generic multiplicity bounds from more than 2 to exactly 4. Similarly, main engine is defined by V8 engine and subsets the inherited engine's usage. This designates it as a specific subset of the inherited engine's collection, narrowing its allowed type to be specifically a V8 engine while obeying the inherited structural rules. Now, there are 3 core concepts that we need to understand by looking at this code. First, abstract usages as placeholders. When we mark the part usages, engines, and wheels as abstract inside vehicle, we are signaling that these are intentional architectural placeholders. They are not meant to be directly realized as is. They exist to declare an architectural rule or structural bound that must be fulfilled by concrete subsetting in a specialized configuration, like sports car does. Second, what subsetting actually means. When we write part myEngine V8 engine subsets engines, we are asserting that the values of main engine are specific subset of the inherited engines collection. It's not completely replacing engines in the namespace. That would require the redefines keyword. It's designating a specific element as belonging to that collection while narrowing its allowed type. Third, multiplicity logic. In SysML v2, the default multiplicity of a nested part is exactly 1 only if you don't explicitly mention the multiplicity and the usage has no explicit owned subsettings or redefinitions. Because we wrote part car wheels subsets wheels with an explicit subsetting, it violates that default rule. If we had not specified a number, it would inherit the parent's multiplicity, which is 2 or more. We write 4 to be explicit. The number makes the constraint precise, and that precision is the point. Now the question is, why does this parse tree structure matter? Because it directly drives how your model is understood. The nesting, the abstract placeholders, the subset relationships, all of that textual structure carries real semantic weight. And when you load this code into a compliant SysML v2 tool, the tool reads that structure and reflects it back to you visually in what the standard formally calls the tree view. This is the central promise of SysML v2's textual approach. The code structure and the underlying model structure are one and the same. Before we wrap up, a quick side-by-side recap with v1. While v1 primarily used the black diamond line on diagrams to show ownership, v2 provides textual nesting inside curly braces as a perfectly equivalent alternative. Furthermore, subsetting, which relied on the subsets constraint string attached to properties in v1, is now elevated to a native core specialization relationship in v2 with its own keyword, which is subsets, and operator, which is : greater than sign. This handles narrowing types or multiplicity cleanly and formally as a part of the abstract syntax. That is the power of SysML v2's compositional approach, a clear, text-driven hierarchy that is both human-readable and tool-ready. In the next lesson, we'll look at a SysML v2 keyword called the port def, and how that gives us a clean and consistent way to define interaction points between parts. We'll explore how that works and what it means for the way you model system interfaces. See you there.